The compiler does not recognize hexadecimal numbers, only decimal. Yeah.
I get it for the coefficients, scaling the coefficients.
Uh-huh.
What do you do for the audio signal which is coming as input, which is 16 bits? I mean, how do you treat that? Is it like a fraction?
It is a fraction. Yeah, the 16-bit audio signal coming in is normalized to plus minus 1. And so you should treat it as a 1.15 fraction, where the 1 bit is the sign bit and the binary point is right here. So think of it as a 15-bit fraction. Clearly, question back there? Yeah. Clearly, you're going to have to extend this 16-bit number to 18 bits for the CPU. You can do it in 2 ways, 3 ways. You could put the 2 extra bits here. You could put 1 bit here and 1 bit here, which would be odd. Or you could put 2 extra bits here to extend the 16-bit audio into 18 bits. The trade-offs. If you make 2 zeros here, then you've maintained as much precision as you possibly can at the risk of overflow. If you put 2 sign bits here, you have to copy the sign bit from here into the top 2 bits, obviously. Then you keep all the bits of precision of the input. You risk some round-off error during the arithmetic, but you have better overflow characteristics. If you put a sign bit here and a 0 here, you have some hybrid of the two. You can use anything you want, anything that works. Any questions about arithmetic systems? Modifying the multiplier. Darwin.
Since the signals from the codec are signed, does it automatically do the last one and just feed it in without doing it?
No, you have to do the sign extension yourself.
Even if the wire is signed?
Even if the wire is signed. If you concatenate bits, because you're going to have to explicitly concatenate bits, right? So you're going to have some audio in signal here, which is 16 bits, and you're going to have to prefix on it 2 bits. Let's see if I can remember the syntax for that. You do bracket, you do 2 bracket odd in 15, I believe, to duplicate a bit twice.
Verilog doesn't complain if you just feed an audio in to the
Nope.
one of the input ports?
No, but it'll do the wrong thing. Because if you just feed audio into one of the input ports, the default in Verilog is to align the low order bits, not the high order bits. And so the sign will be incorrect and you'll get full wave rectification and it'll sound like crap, to use a technical term. You'll get a lot of crackling and go shh instead of sounding like a sine wave. You'll hear the sine wave. You'll actually hear the second harmonic as a sine wave. And you'll hear a bunch of crackly sounds due to all of the discontinuities in the waveform. So you have to explicitly sign extend if you decide to write justify it. What have people done so far? Right justify, left justify, or split the difference?
Right justify kind of it reduce the distortion, but no. Right justify, it reduce the distortion. The second one, yeah. But we got some crackling. We're trying to reduce that. It's filtering, but it's filtering with a little bit of distortion.
So there may be some overflow.
Actually, yeah. There's definitely overflow because at the lower order of the waveform, it kind of peaks out like this.
Okay, so if there's overflow, then you might want to go to this situation. Any other comments about this? You tried something that worked or didn't work? So you used this scheme, and that certainly does avoid overflow, particularly if or tends to avoid overflow. I think for the particular filters I specified, the coefficients are all in the range of plus minus 2, less than or equal to the absolute value of 2. And so if you're shifting this fraction down by 4, then you should certainly avoid overflow. You're shifting 2 bits, you multiply by 2, you should still have a bit to spare. So that should help with overflow. Anything else on arithmetic systems here, or filter conversions? Now, there is this other thing you can do to avoid overflow, which is to scale the coefficients of the filter. So we have this A1 yn is equal to B1 xn plus so on. And if the B's and A's are too big, greater than 1, for instance, then you could divide this whole equation through by 0.5, say. Divide by 2, there we go. Divide by 2, which means we divide A1 by 2 and B1 by 2 and all the other coefficients by 2. And then the last step in the filter is you calculate this sum divided by 2, and then you shift 1 bit to the left, 1 bit to the left. So you can avoid some overflow, because quite often in the filter there will be a fairly large product which is negative and a fairly large product which is positive, and those cancel to near 0, and then when you shift back to the left by 2, you do not get an overflow. Any questions at this point? Find any bugs with the compiler? Any annoyances with the compiler? Oh, I'm sure there's some of those. Well, the error feedback is a little cryptic. It's either cryptic or non-existent. Don't make mistakes. Right, that's the But for instance, if you say something like out 3 equal out 3, you get a completely obscure reference that says push I requires a argument. Requires argument. And that's because if you use the equal sign, it tries to parse the out as a variable name. It doesn't exist, so it can't push the value onto the stack. All right? Don't do that. It turns out getting good error reporting in a compiler is harder than writing the compiler. It's really difficult because you have to keep all kinds of state information to know what's legal and what's not legal. And I'm working on it. I recognize this as a deficiency. It gives me new respect for GCC. It gives me a lot of respect for GCC. Okay. Anything else? On Lab 2. Okay, well, let's move back to Lab 3 then. We went through the algorithm, the basic update algorithm for Lab 3 last time, which is going to be an iterative solution of a partial differential equation, numerical iterative solution, and there's a couple of more things I want to talk about this. One is more about the algorithm and the Matlab version of the algorithm, which takes the formulas and turns it into procedure. But also, we have to talk about the trade-offs in parallelism versus sequential calculation. Because the calculation at each node is fairly simple. It's something like 10 arithmetic operations for each node for each time step. And you figure that conservatively you can clock the state machine or the CPU or whatever you use to calculate this. You can clock at 50 megahertz, and the audio sample rate is about 48 kilohertz, which suggests that you have something like 1,000 cycles of the CPU per audio time step. So, if it takes 10 operations to do some arithmetic, so you have to do about 10 operations per update. By the time you retrieve from memory and store to memory and do the actual arithmetic and scale stuff, I would say we're probably talking about 50 to 100 cycles per node update, where a node is one of the points on the drum head that we're going to be calculating that we talked about last time. And you have to, the spec in the lab is you have to update at least 100 nodes per audio cycle. This would suggest that each state machine or CPU or whatever you use to calculate this should update something like 10 to 20 nodes. If you want to pack as many nodes into each CPU as possible, which you should do because you're being graded on the number of nodes you can update. So you got to pack in something like 10 or 20 nodes per CPU, something like that, to keep it busy. Now, if you clock faster, and I think realistically you might be able to clock a state machine up to 100 megahertz. If you decided to use these, what are we calling the CPU now? Short stack? If we decide to use the short stack CPU to do this, then you could probably clock this at 65 or 75 megahertz. So you have a constraint that to get the maximum number of nodes in, you're going to have to do some serial calculations. All right. On the other hand, it's pretty clear that even if you build a fairly big optimized CPU that could do this calculation very quickly, you would have to do 100 nodes, you would have to get this down to 10 cycles per update on one CPU. You might be able to do that by pipelining it. And then you could have a uniprocessor running, but with a weird instruction set. A weird instruction set that had instructions like add 4 nearest neighbors together. You might also be able to figure out a way of duplicating memory, so you have multiple copies of the grid, so that you can do 4 memory accesses in one cycle off of 4 copies of the grid. Because you got lots of memory, right? You got the 104 M4K blocks. Why not make multiple copies of the grid so you can do multiple memory accesses at once? Maybe you could get the number of cycles down to 10 per node update. Maybe you could even get it less, because some of the arithmetic can be done in parallel. Maybe you get it to 1. Nah, probably not 1 cycle. Maybe 3 cycles. Then you could do 300 on a uniprocessor, but it would have to be a fairly complicated processor that you built. It's your choice. You can do it any way you want. My guess is that most people are going to go for some trade-off between a fairly simple serial processor and build lots of them, versus building a really complicated pipelined uniprocessor or very, very simple single node processors. It's an interesting trade-off. You could go, the other side of this is that if you go to multiple processors, you have to worry about communication between them. And there's going to be some communication overhead. If you go for completely parallel communication overhead on a single node basis, you can do an awful lot of updates per second. You could update this probably every 20 or 30 times faster than you can produce audio samples, so that's not useful because you can't hear it. Oh yes, I should say also, the default rate for the audio codec as written is around 48 kilohertz. I think it's actually 47. You can double that to 96 kilohertz if you want, or lower it as low as 8 kilohertz if you want more time to do samples, because what you're being graded on is the product of sample rate fs times number of nodes. So if you found that it was handy to build a simpler machine, a simpler state machine that you didn't want to make very serial, then you could up the rate here and still play it back through the speakers. The simplest case is you update one computational node with communication from the 4 nearest neighbors. But you can clearly do better than that. If you said one computational node was going to update, one computational unit was going to update 4 nodes, then the parallel communication you need out only requires 8 lines. So you get a little bit of, now you're doing 4-way calculation. You would update these sequentially in a sequential machine, and then update the I/O lines sequentially before the next time tick. So here you would have a 4-way serial followed by a 4-way, 8-way update, communication update, and then the next clock cycle would start. Well, maybe it's better to do, well, I said 10 to 20 nodes. Maybe it's better to do a 4x4 array. So we're going to update a 4x4 array of nodes in serial, going around here, updating in serial, and then having parallel communication out of 16 wires. Well, at least now we only have 1 wire per node. That's good. Here we had 4 wires per node. Now we have 16 wires. We have 1 wire per computational node. And the number is about right. It's somewhere between 10 and 20 nodes. So you could imagine building a state machine that steps through 16 memory locations, updates 16 computational nodes on the grid nodes, propagates the values out either in parallel or in serial to the nearest neighbors along the X and Y direction, and that could work. Another possibility is taking now the whole grid here. We have this whole grid, let's say it's 16 by 16. We break it into 4 parts, and we build a serial link that goes across each one of these. And we don't try and communicate in parallel with lots of wires. We have one 18-bit bus between these 2 processors. So this is an 18-bit bidirectional bus, 18-bit bus, and each processor now updates an 8x8 array. Well, that's 64, 8, yeah. That's a little high, but maybe it would work. Maybe if you optimize the instruction set and the memory accesses, you could get 64 updates per CPU. Maybe if you drop the sample rate to, instead of 48, drop it to 22, so you have a little more time, which it allows you to get a better use of serial in a given computational unit. So you update 64 computational nodes here, and then serially communicate them over to this CPU before the next time step. Reduces the number of wires enormously, because now it's all bus based. It's going to take longer because there's no inherent parallelism, but maybe that doesn't matter. Maybe you get enough efficiency of scale or maybe you should go to a hybrid, a completely different layout. Let's say you made a linear array of CPUs so that you had one-dimensional nearest neighbor connectivity, but you cycled the rest of the array was cycled through this line of processors so that the whole grid gets updated in order n, where n is the size, if this is n this way and you have n samples, you would update the whole grid in n time steps by passing it through a linear array of updaters, where this direction has spatial nearest neighbor communication and this direction has time nearest neighbor communication. In other words, you have to save the last one before and retrieve the one. You save the one above and you retrieve the one below. And this would work well if you had 16-way memory, where you could grab each one of these samples. If this were 16, if you had 16-way memory, you could grab the next sample to be calculated from 16 different M4K blocks and do all those memory accesses in parallel and save an enormous amount of time. So you have lots of choices about topology, connection topology, the amount of serialism, no, the amount of serialifying, the amount of serial computation you're going to do in each node. Serialization, right? Anybody had any thoughts about this yet? This is going to be your first design decision, is how you're going to decompose this problem into computational units. I have seen all of these used, and they all work. There's also some weird tricks you can do. One group, a couple of years ago, maybe last year, noticed the following symmetry. If you have a square drum and you hit it directly in the center, then you have symmetry. This half has to do the same thing as this half. This half has to do the same thing as this half. And so you really only need to compute 1/4 of the nodes and get the boundary conditions right. The boundary conditions, you only compute this quarter, but the boundary conditions are now, this side is held still, u equals 0, and these two sides have du dx equals 0, and this side has du dy equals 0, because you have to have continuity across the break. And so you can simplify the computation at the expense of messier boundary conditions. So, you can do it any way you want. There's some examples online of the sounds that are made by various drums that the students have built in the past. I can't think of any other architectures that have been used. In addition to the CPU you're using in Lab 2, short stack or whatever we're going to call it, there's also a NIOS 2 MIPS-like CPU with floating point that is available. I would suggest you not use this on this lab because the learning time is about a week. That's why Lab 4 is 3 weeks long, so you have 1 week to learn how to use the NIOS 2 and 2 weeks to do the lab. But you could also change the arithmetic unit in the short stack machine to be floating point. There's an 18-bit floating point that was written by Skylar Schneider, thank you. Skylar Schneider last year, that you could bolt into that CPU if you wanted. It's not a single cycle multiplier, it's a 2-cycle multiplier and a 2-cycle adder. So you'd have to change the state machine in the CPU to put it in an idle state in a multiplied and add instruction. But it wouldn't be a huge job. Or you could use the 18-bit floating point and build your own 16-way state machine that cycles through the computational states for 16 different nodes and computes floating point answers rather than fixed point answers. Does anybody have any opinion on these? Does anyone look more straightforward than the others? Anyone say, that's the way I'm going to do it because it fits my brain? Right. So let's talk more about algorithm then. Any questions on this? No. Okay. There are lots of design trade-offs in this lab. And there is no right way to do it. There's a lot of wrong ways, but there are also a very large number of correct ways of doing the lab. So, gives you the choice of playing with all kinds of parallel architectures. But I suggest you choose one fairly soon, like before this weekend or during this weekend, and start implementing it. So I gave you an example on the website of a serial implementation because I don't know about you, but the way I go about designing stuff is I write it in Matlab in serial, and then I take the Matlab and I convert it to C in my head or sometimes on paper. In other words, I devectorize it. I take all the vector notation out of it, and then once it's in C, then it's not so hard to put into Verilog. But what I'm going to give you is the fully vectorized version here, and which outlines the algorithm pretty well. First of all, I'm calculating a 16 by 16 grid. No particular reason why it has to be square, but in this example it is. And Matlab has this interesting feature that if you pre-allocate an array, the program runs much faster. And so all of the arrays are pre-allocated where U is the current time step, U1 is time t minus 1, and U2 is t minus 2. And since we're starting all of these at 0, we're starting the drum head at 0 velocity. If these were different, then there'd be an initial velocity on the drum head. There's going to be some parameter rho that we talked about last time, which is proportional to C times dt over dx squared delta t over delta x squared. And for stability, 0 has to be less than or equal to rho, which has to be less than 0.5. It's kind of the speed of sound, normalized speed of sound on the drum. And there's going to be a eta, which is a damping coefficient, which I'm going to make quite small here because I want the sound to last for a long time. I want the drum to resonate. And we're going to have a boundary gain, which is a reflection coefficient, or how much the boundary changes when energy hits it. And we're going to set the boundary gain to 0, which means in this case the boundary is fixed. It does not move. FS, I set to 8,000 to make the calculation faster. That's the sample frequency. Windows is a little picky about sample frequencies, but Matlab isn't, because it does the right interpolation. But 8,000 is a standard Windows kind of frequency. And we're going to define a time vector which goes from 0 by 1 over Fs to 5.0 seconds. And we need an audio output, AUD output. And this is going to be a big array. And it is important to zero this for performance of size time. And using the size time construct forces this audio output file to be exactly the same size as the time vector. And that's useful if you're going to, say, plot it versus time. The next thing we need to do is to calculate the initial strike. And if we look in one direction of node 1 versus node n, what we're going to do is we're going to approximate a Gaussian for the drum strike. And the reason for using a Gaussian to approximate the drum strike is that a Gaussian has a very nice spectral property. Does anybody remember what it is? Fourier transform of a Gaussian is what? It's still a Gaussian. And so the spectrum is very smooth. So we're going to say that if we have some center here where the hit is, that the displacement of the membrane, you're going to smack one node, but the membrane is going to displace Gauss in a Gaussian fashion, so that the displacement due to the hit is going to be given by some amplitude, which you get to choose, times e to the minus r squared, where r is the distance out from some point, and this is therefore amplitude times exponential of, oh, we need some scaling factor alpha in here, which is the width of the distribution. It's the exponential of alpha times x minus x hit squared plus y minus y hit squared. So a big alpha means a tight distribution. A low alpha means that the drum is going to respond very flexibly and be deflected all over its surface. The bigger you set alpha to, the narrower the distribution and the higher the pitch of the tone, because you're applying more like an impulse and you get more higher harmonics. So now to take this to, well, I don't need to take that to Matlab code. I don't think. Any questions about this? For purposes of conversion into Verilog or assembly language or Pancake or C or whatever you decide to use, you're of course going to not compute a full Gaussian. You're probably going to have a couple of tables that you use. You're going to have a couple of tables, one of which says that the strike point is given by unity amplitude, and the one next to it on each of four sides is given by amplitude, by 1, 1/2, and the next one is 0 or 1/4. But you're going to have a small table that you're going to use. Although you could calculate something like a Gaussian. So what remains to be done then is to step forward in time by given the initial condition of a hit, and the boundary conditions that the edge of the drum is always going to stay still, we have enough information to solve the system, and all that remains is to step forward in time, one step at a time, and calculate it. Now, since this is a linear system, you could do it analytically. However, you probably don't want to. Any of you remember what conformal mapping means from complex analysis? You can solve any shaped drumhead that's bounded by a polygon by conformal analysis, conformal mapping. And that was used. There was a conjecture 15 years ago that no two drumheads of different shapes made the same sound, or differently, that there are no two drum heads of different shapes. Yes, would make the same sound. And using conformal mapping, a group here at Cornell managed to analytically prove that there were two different drums that made the same sound. Obsessive. I like it. So start thinking about what fits best into your brain for doing parallel computing here. This is a nice parallel computing problem because every computational node takes the same operations. The same operations occur at every node, which means that getting all the nodes to finish at the same time is trivial. You don't have to synchronize. There's no synchronization step necessary. They all do the same operations and finish, and you're ready to output another sound sample. Lab 4, but there is communication. This is not trivially parallel because each neighbor has to talk to its nearest neighbors. Lab 4 is going to be the opposite. It's going to be a trivially parallel operation in the sense that you're going to have to update about 1 million pixels, and each one of them is independent of every other pixel on the screen, but each one takes a different amount of time to update. And so you will have no particular communication between processes, but to make the thing finish as fast as possible, to make the whole calculation finish as fast as possible, you're going to have to load balance, which means that processors that get easier jobs are going to have to do more of them. So it's a different kind of limit of parallel computation. Any questions? So Lab 2 is due Friday. Feel free to stop by my office tomorrow. I'll be in lab all Thursday afternoon working with another course, but I'll have time to answer questions. I get multiplexed pretty well. And don't hesitate to email me if you have a question, or if you find a bug in the compiler. in Pancake. All right, let's get out of here.